All right. So hello, class. Welcome to Lecture 7. So this Lecture 7 begins a series of lectures stretching from Lecture 7 all the way through Lecture 11, although Lecture 10 is really the culmination of this series. All right, so we've got Lectures 7, 8, 9, 10, 11. And this is the section of the course on optimal control. This will be followed, of course, by the courses on robust control afterwards, nonlinear, /SOS. And then, depending on how far we get, we'll talk a little bit about hybrid systems. Maybe. So, when we have the course title here, of course, it's optimal and robust control. So, this series of lectures is the optimal part of that, optimization of the control. So, we've introduced optimization per se, in terms of vectors and functions and all that. So we've defined what optimization is. So we're in a good position to start talking about optimal control. Not robust control yet. We'll get there eventually, later. But so these series of lectures is really the heart of this course. And after lecture 11, that's when we have the midterm here, which is actually going to be fairly late midterm, but we'll see how that goes. And then we'll do robust and nonlinear and stuff. So this is more advanced stuff. But this is the core of the course, right? So in this lecture in particular is critical to understanding the remaining series of lectures. So if you don't understand what's going on in this, don't be surprised, right? This is in many ways the hardest part. You'll have trouble with 8, 9, 10, and 11. So I might even suggest you watch this twice or really focus on this aspect of the course because it sets the stage, right? There are not that many results per se which are usable in a certain sense, but it's the mathematical heart of the rest of the lectures. These are sort of extensions of combinations of what we covered in lectures 1 through 6 with the mathematical material we cover in lecture 7. So what are we covering in this lecture? And it's really important. And it really almost is a repetition in some ways of things you already know. Maybe you learned from undergraduate controls, right? With transfer functions, and block diagrams, and Bode plots, that kind of stuff. But 9 times out of 10, or perhaps 99 out of 100 times of 10, these things are defined in undergraduate controls in sort of an ad hoc way, right? Sort of a hand-wavy type approach to these topics. And that's not going to cut it if we want to be optimal, right? If we want to formulate this thing as an optimization problem. Because remember what I said earlier is that setting up your optimization problem is 9/10 of the problem, right? So in that way, lecture 7 is, in a way, 9/10 of the problem, right? And then we find ways to solve the problem, using our various optimization techniques in the other lectures. But this is an important one, right? So I'll come back to block diagrams, and I'll come back to transfer functions, and what you've probably seen, right, or things like this in your undergraduate course, right? You got a system G here, or maybe you even go far as to write it as g of s, right? The transfer function, right? You write these block diagrams in transfer functions, you close the loop, you put another transfer function there, and you close the loop on it. And so the idea, right, is if there are no poles in the right half plane or something, you've done well. Well, why is that? What do poles in the right half plane have to do with anything? And what are even these things? Why are we writing down this block as a transfer function when it's really obviously a system, right? These are interconnected systems. Is this a system or is it a transfer function? And then what are these signals? Well, we talk about them, right, as U, right, as signals. Actually, that one's probably Y. This one's U. And so what does this block diagram even mean, right? Well, presumably it means that Y equals G hat times U. Well, what does that mean, right? So in this section, in this lecture, we're going to we have to go through and we have to rigorously define everything. And well, of course, we would know what this block diagram would mean if these were all matrices, right? So if this was a matrix G, right? And this input was a vector, right? That was in Rn, and this was a matrix in Rm times n, and the output was in Y and Rm. Those are vectors, right? Well, we know that Y equals Gu. But they're not. They're not vectors. They are functions. Functions, not vectors. And this G is a system and not a matrix. And it's not a transfer function either. It's a system, right? So what do we mean by transfer functions? How did we get from a system to a transfer function where we can write things like Y hat of S equals G hat of S, U hat of S? Well, it turns out it depends a whole lot on how you define your vector of functions and how you define the norms on those functions and the size of those inputs, because these block diagrams don't make sense except in a very, very specific particular context. And that's what we are going to go over today in this lecture. So that's the goal here, and it's not trivial, right? It's rather tricky, and I try and distill it out to the bare essentials, the things that we need, but it's still tricky. And normally we would have an entire linear systems course on this subject, but we don't have time for that. So we're gonna have to skip a few things. Okay. So let's start off with the signals, right? So again, the picture you have in mind is that of the block diagram, where we have a system G, an input U, and an output Y. Now, as I said, Y and U are functions. They're not vectors, they're functions. So U of t, Y of t, all right? And they're somehow related by this system G, which maybe is state space or maybe not, right? It's some system which maps a function to another function, right? So let's start with the functions, and then we'll talk about the systems. So what are the functions? Where do they live? How big are they? How do we define them? How do we parameterize them? Well, these are all good questions, right? So we'll come back to we talked about earlier, which is vector spaces, right? Vector spaces. So we've sort of been alluding to this earlier, that these signals lie in a vector space. But what is that vector space? Well, a vector space doesn't have really any structure, it doesn't have any size associated to it. So we want to establish performance properties of the system, right? We have to talk about sizes of the inputs and size of the outputs, because otherwise what are we optimizing, right? It doesn't make any sense. So that's an important concept. And to enable that, we define norms on these vector spaces. So the size of the input is we can define with a norm. Right? So remember, these inputs, they don't go away. They last forever. Right? They're defined on a time which lasts forever. Time goes from 0 all the way out to infinity. Right? Infinity is not a number, so it just keeps going. Right? So how do we define a norm on a function which lasts forever? Right? Well, that requires us to think carefully and define carefully what we mean by a norm. Right? So a norm has a very particular, very specific mathematical definition. Right? So specifically, it has to satisfy 3 properties. It's a map from the signal, or from the vector space, to a real number. Right? That's not a property, that's just a fact. Right? That's what the norm does. Maps a function to a vector. And we should write v here. So what properties does it have to have in order to deserve the title of norm? Well, they're relatively obvious, but it's important that we go through them in particular because only these 3 properties are needed. First of all, functions which are 0 get mapped to 0, and functions which are not 0 don't get mapped to 0. That seems relatively obvious. So basically, a function, a vector, its norm is 0 if and only if the function itself is 0, which means, in our context, that the function has to be 0 for all time. Now, when we get to Lebesgue integrable functions, we can allow them to be non-zero on finite measures, like instantaneously, because, well, that's just too complicated to get those instantaneous changes. But the integral, right, of a function is 0 if its integral is 0. So basically an integral, right? And how we define the integral is important, and we have various concepts of that. But the integral of u of t is 0. So obviously, if u of t is not 0 on some non-zero time interval, then this integral is not 0. So this is how we may define zeroness for these functions. The second property is the scalar multiplication property, basically. So basically, if you have u of t, a function of u of t, and you multiply every point in time by a scalar a, and then you take the norm of that. Here we should put a little c dot here, not the instantaneous value of that function, but the whole value of the function, multiplies at every time instance. Well then, the basic property of the norm is that the absolute value of that scalar times the norm of the function itself, right, is equal to the scalar multiplied by the function. It's a fairly obvious property, right? And there's very few norms we could think of which don't satisfy that. But it is something that we have to define and something that we can use later on. So next, those are 2 relatively obvious ones. One is the most obvious, 2 is the second most obvious. The third is not entirely obvious. So it's the Pythagorean inequality. So not Pythagorean theorem, right? So the Pythagorean theorem actually requires more structure, right? That allows, Pythagorean theorem requires us to have a concept of perpendicularity, which we don't have quite yet. We don't need that quite yet. We'll get to it later. So we say u and w, u and y are perpendicular in a certain sense. We need an inner product space for that, but that's not norm. However, right, so that if they're perpendicular, that implies, of course, u plus, the Pythagorean theorem says u plus v, that norm, is equal to u plus v, and squares there, right? The square of the hypotenuse is equal to the sums of the squares of the sides of the matrix, right? For a right-angled matrix, perpendicular matrix. We don't have that yet. We have the inequality version of that, saying that the hypotenuse has to be less than the sum of the sides of that triangle. Right? So this is a you know, a less obvious restriction on our norms, but it's actually gives us all the structure we need to be able to define a norm effectively. And without that, the norms that we would define would be relatively useless, and none of the results that we could present would hold. So that's an important one. Right, so that's the properties that a norm has to satisfy. And remember, we're thinking of function spaces, or in discrete time, we're thinking of sequence of values of those signals. So these are signal spaces. And so here's some norms, and this is not, and of course, a complete list, but there are other norms you can define on function spaces. But these are the ones we work with most often, because, well, they're all sort of Banach spaces, which means the norm space has certain properties that sequences in that space converge to elements of that space. But we don't need to get into that, really. So there's several ones which we list here, the LP norms, right? So these correspond to different values of P in the sort of subscript here. And they're all denoted with a norm and then a subscript on that norm, L1, L2, and so forth. And they're all sort of variations of each other. So particularly, they're all variations of the most general P norm. And that's the norm where you take the pth power of the function, and then you take the square root, you take the integral of that, and then you take the pth root of that function itself. Right? So that's an important one. And then we can generalize that to take special cases of that. So the most important special case, of course, will be the L2 norm. And that's where we take the square of the function and the integral of the square. So the square integral of the function, and then it's the square root of that square integral. Right? And of course, we can put a square here and get rid of the integral entirely, but that's not how the norm is defined. Right? So don't forget the square root or to square the norm of the function itself. So that's the most obvious one. It's the integral of the motion of that function over all time. And notice it is from 0 to infinity, so over all time. So functions which look like, for example, this, so assuming they decay down to 0, are generally square integrable. So negative exponentials, for example, right, are square integral. You can integrate that function for all time. Other functions are not square integrable. So for example, the step function is an important case, which is not square integrable because, right, you're integrating the square of, say, 1, for example. This is 1. Square 1 is 1, and then you integrate it from 0 to infinity, and the L2 norm of that would be infinity, right? Because you never stop that limit of integration. So these things have to converge. They have to have finite energy to be in these signal spaces. So it's important that all of our signals have finite energy. Another obvious case where we don't have finite energy is a sinusoid. A simple sinusoid like that goes on forever, never decays. And so we integrate this bit, integrate that. Those are all finite, but we have to keep going forever and ever and ever and ever. And so we keep getting more bumps that we have to integrate. And so ultimately, the L2 norm of that is also infinity, right? So not in L2 and also not in L2. By the same logic, both of those square step function and the sinusoid are also not in L1 or in any other P norm except infinity. And we'll come to infinity as a special case in a minute. Because by the same logic, right, this term never goes away, right? It never fully disappears. And so when you integrate from 0 to infinity, none of these signals have finite energy. They just keep oscillating forever in the case of a sinusoid, or they just keep building up forever in the case of a step. Right? So that's a problem. One signal space which we don't work with much, but can actually allow for these types of signals is the L infinity norm. Right? This is the space of bounded functions. Right? So if you take the limit as p goes to infinity, right, this gets very large, but then the square root also gets very large, and so those tend to cancel each other out. And ultimately what you get is that the infinity norm is just the maximum value of the function over its entire life. So it doesn't matter how many times you get back up to this infinity norm. The infinity norm doesn't change. If you were to like bump up against, go beyond it again, then the infinity norm would be up there. Right? But and likewise with the step function, right? The L infinity norm is 1. But like I said, the L infinity norm is rather hard to work with. Right? We have very few mathematical results or rigorous results which allow us to do much of anything for signals in the L infinity norm. Right? So despite the fact that you've seen a lot of, in undergraduate controls, a lot of stuff done with step functions or sinusoids, that work is actually all not rigorously represented in the block diagram structure. So step functions and sinusoids are actually not allowed in terms of our signal spaces. Right? So for us to have a well-posed system, we assume that all of our signals have finite energy. And that makes sense, right? If you think about it, if you give, say, an impulse is well-defined usually. If you give an impulse to a system and the output you get is a sinusoid, basically what's happening is you're taking a finite energy kick to the system and you're producing an output which has infinite energy that goes on forever. So we don't really believe in, what's it called, perpetual motion machines. So we don't consider this to be a well-posed system. Right, and so that distinction is very important. Finite energy systems. So these are all these norms are sort of notions of energy, how much energy is contained in that signal. What's the gain from the energy of the input to the energy of the output? And it turns out that's what we're going to be optimizing for the most part in optimal control. Each of these, by the way, of course, extends to the discrete time framework, right, where we've just replaced the integral with a summation. Right? And here we've replaced the sup with a max. That max just is the same version of supremum, where we just have finite number of things we're checking. And here we're sort of looking at every point, right? So infinite number of points versus a countable number of points. Right? So the difference is in discrete time, right, we have a sequence of signals, right? So we have input which goes here, 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 I don't know, here, something like that. And then instead of integrating that, because there's lots of white space in between those two, or green space in this case, we take the sum over all of those points. And so the little L1 norm, so the L in LaTeX, little L1 norm is the sum of the values of all of those signal values. Of course, the L1 norm is actually the hardest to satisfy. Convergence in L1 norm is extremely rare. L2 norm, the little L2 norm, right, for discrete time systems is a square of the sum of those values of time with a square root. And then we can generalize those to the little LP norm and the extension to the infinity, little L infinity norm is just the maximum value of those elements. So these signal spaces, these norms, right, give us a concept of energy of the signal. And if you think back, of course, to Lyapunov functions, we sort of talked about Lyapunov functions in terms of the amount of energy remaining in the trajectory, right? We can now define Lyapunov functions for different LP norms as well. Oh, sorry, ran over there. Energy and trajectory. Right. So that's the basic what we mean. These are the basic concepts of inputs and outputs, right? The signal spaces. So now I have a rather lengthy discussion here of some things which you probably want to read. So a way to think about these norms, right? The L1 norm, the L2 norm, and so forth, right? As relatively straightforward generalizations of, say, the Euclidean norm, right? For vectors, right? So you think of these signals as generalizations of vectors, where instead of indices, x1 down to xn, we have an infinite matrix. So in little L2 norms, x1 down to x infinity, or in the continuous functions, we have x of 0, x of t1, down to x of infinity, right? So we can think of them as lists of values of the signal, right? And so then if we think about that in the proper way, then these norms are just nothing more than the straightforward generalizations of the norms we have for vectors, right? So the size of a vector, right, in this case, right, what is that? Well, that's the sum of I to k, or n, right, of xi squared. That's the standard Euclidean norm, right, that we use all the time. So it's useful to think about these signals as generalizations of vectors. And so then the obvious implication is that if we're connecting these with block diagrams, we're mapping a signal to another signal. The obvious implication then is that we're going to start thinking of systems as the generalization of matrices, right? And so when we talk about all these matrix properties, when we talked about linear algebra and all this stuff, all of those properties have a generalization to systems. So everything we define for a matrix has a system-level generalization. So really the purpose of this lecture is to define those generalizations, to take all those properties we have for matrices and extend them to systems. Take all those properties we had for vectors and extend them to signals, right? So matrices, matrix properties, go to systems, and then the vector properties go to signals. Right. Okay, so that's the big picture. And now, how does this fit into our theme of representation of the system in terms of A, B, C, D versus the system itself? So there's the representation. Well, how do we represent a sort of a vector in infinite dimensional space? How do we represent these signals? How do we represent the systems, right? So obviously in the first few lectures we talked about the state space representation, right? Which is one representation of the system. Really what we're interested in is what happens to signals when they get mapped to the output. And so there are alternative representations of this which are quite useful, and you've probably learned about it. One such is the transfer function. A transfer function is a way of encoding what happens to the input as the system acts on it and produces an output. And it's more direct than the state space representation. It tells you more directly what happens to the inputs as they get mapped to outputs, but only in the frequency domain. And that's something we have to define more carefully later. And furthermore, the size of these matrices A, B can have absolutely no relationship to the size, say, of a system, right? To the gain from inputs to outputs or other properties of the system. Whereas the transfer function representation does have useful interpretation in terms of the properties of the system. And so transfer functions, well, they were, of course, limited to undergraduate control. have a use in optimal control. And so we will use them to a certain extent. And in particular, there are various norms defined on transfer functions which translate to norms to the system. Okay. So we'll talk about that later on. Right? I'm not going to read through the entire description here, but I encourage you to do so after the lecture. So now we've talked about the size of signals, and presumably we would like to design our system to, say, minimize the size of an output given a finite energy input, or something like that. So norms are useful, but they're not. It turns out they're not quite enough, right? Because vectors have very useful properties that functions in these generalized norm spaces often do not. And in particular, vectors have a very clear notion of perpendicularity, of angle between vectors, right? If I draw a picture, right, here's vector 1, here's vector 2, or x and y, maybe better, right? It's very clear to me, right, that I can determine there's a notion of angle between those two vectors, how close they are to each other. And that measures, say, if it's less than, theta is less than 90 degrees, x and y are more or less pointing in the same direction. And if theta is greater than 90 degrees, they're more or less pointing in opposite directions. And here I should say that greater than negative 90. Less than negative 90. Right? So this notion, this structure on the space, which allows us to tell if signals are pointing in the same direction or opposite direction, so the law of sines, for example. And in addition, right, it gives us this notion of perpendicularity, right, so that a vector is perpendicular to another vector, right, if x transpose y equals 0, right? And that corresponds to the case where theta is 90 degrees. Those are at 90 degrees to each other, right? And, well, you might ask, is this something you even need to worry about for a vector? Well, I mean, intuitively, it seems like it might be tricky, but it's important, right? So, for example, we could say that two sinusoids, right, are perpendicular, right, if they cancel out each other, or they're at 180 degrees, right? In this, you could think of them as phase then. If they're completely out of phase, right, that's an angle. If they're completely in phase, that's an angle, 0 degrees. If they're 90 degrees out of phase, we say they're perpendicular, right? This is theta equals 180 degrees. Right, so there is a precedent for a notion of angle between function spaces, right? The phase between two functions, right? So magnitude and phase. So it's not we're not coming out of left field here, right? So the idea that there is a geometry on these function spaces is not entirely useless. And so in that context, then let's define what we mean by a suitable angle. Right? What does it mean for there to exist an angle between two vectors? Right? And so that concept is that of an inner product. So a generalization of this transpose that we have for vectors. So that x transpose y is, those are perpendicular if it is 0. Well, we're going to generalize that transpose idea here to this bracket notation here, right? Which makes more sense for functions because we don't really have the idea of a transpose of a function. That's not something we can really work with. So we don't have quite the same structure as don't require quite the same structure as for the vector space, Euclidean finite dimensional vectors. But we have an alternative way of writing these things. So this inner product of x and y, right? And if we have such a thing, and we'll define the necessary properties, then we have this notion of angle, right? Because you just, right, cosine theta equals the angle between two vectors divided by their norms. Right. And then we can take the arc cosine if we like. Right, so if we have an inner product, then we can define an angle between two vectors. Right? Obviously, it has to be a norm space, right? Because we define this angle in terms of norms. So, given a norm space is a special case of an inner product space, or more general than inner product spaces. Not every norm has an inner product for which there exists an angle. In fact, it's actually relatively rare that they do. All right, so let's then define what needs to happen for an inner product space. Basically, not much, but it turns out not much is still asking a lot. So basically, the most important inequality or most important identity for our inner product space is that well, there's some other so like the same properties that hold for a vector space for a norm space have to hold for an inner product, but then one more, right? So for example, the scalar multiplication, right? That has to hold, right? But then one more has to hold, which is the Cauchy-Schwarz inequality, right? So basically, if we define the norm, and the inner product has to be associated with a norm defined in this way. If we define the norm as the inner product of a vector with itself, then the inner product of any two vectors, that absolute value, because remember this can be negative, has to be less than the norm of x times the norm of y. And that's just ensures, of course, that this term right here is less than or equal to 1. Right? Or it's between -1 and 1. Or it's not. This thing is. So the Cauchy-Schwarz inequality is an inequality defined on these vector spaces. Now, additional things like multiplication of vectors are not generally allowed, right? We don't require us to be able to multiply two vectors together. Only an addition property is required. We have to be able to add two vectors together, right? Because that was a basic property of norm spaces. But we don't need to be able to multiply them together. So that's why we sort of move away from this x transpose y, because this looks like multiplication, but it's not really. Yeah. So with this notion of inner product space, then we have the Cauchy-Schwarz inequality, which is mostly by definition. But we also have the Pythagorean theorem, right, by this identity right here. So basically, if theta is 90 degrees, right, then we can prove that the length of the hypotenuse is equal to the length of the two sides, right? And this happens if and only if those two vectors are orthogonal. And this is a basic property of inner product spaces. So with that in mind, let's revisit our candidate norm spaces and ask the question of whether any of these are in fact also an inner product space. If there exists an inner product where x comma x square root is equal to the norm itself. Okay. So it turns out only one of these, well actually two of these, has such an inner product space. None of the others do. Okay. And that one is the L2 norm. Right? And of course, by extension, the little L2 norm. But we're not going to talk about that right now, because we don't want to repeat everything in these lectures for the case of discrete time. But rest assured that almost everything carries over to the discrete time case as well. So the L2 norm is the only one for which there exists an inner product which induces that norm, which means by induces that norm, I mean this, right? That the inner product of u with itself is equal to the norm squared of u, right? And so what is that inner product here? Well, it's fairly obvious what it should be. It's just, right, instead of the square here, which is the Euclidean norm for vectors, because remember, u of t is a vector. So the value at time t is a vector. And so this is a vector norm here. Right? And so it makes sense that the obvious inner product associated with that norm would be the inner product in Euclidean space of u at t with v at t, right? So we take u transpose t and v of t, and we integrate that for 0 to infinity, and that is how we define our inner product space. And obviously, if and actually I need a square root here. No, I don't actually in this case. So that's the inner product. So we integrate that for all time, and that is how we define our inner product. And obviously, if u and v are the same, u and u, right, this is just the Euclidean norm squared, and then we get the norm squared itself, right? So the L2 norm has an inner product, but none of the other ones do. So mostly, we require this inner product space. Almost all of the results that we list in this course and in optimal control in general are only valid for signals which are in little l2. And that carries over as well to the frequency domain. The Laplace transform is only defined. The Laplace transform is a transformation defined on an inner product space. And so there is no transfer function if your signals are not in little l2. If you can't take the Laplace transform of a signal which is not square integrable. It doesn't make sense, right, theoretically. Now the Fourier transform is another story, but we're not going to get into that. So we have one inequality here which is very important, and it's defined on signal spaces. We haven't talked, however, at this point about the system, right? So these generalize vectors. So these apply to vectors, right? This is x transpose y is less than norm of x, norm of y. We haven't, however, talked about matrices. Matrices don't have the same property because there's no, well, there is an inner product on matrix spaces, but we're not going to talk about it very much. It's called the Frobenius norm. But matrices don't really have that same inner product structure, and by consequence, systems also don't have that same inner product structure. Right? They do have another structure, an algebraic structure, which we'll talk about shortly, which looks similar to the Cauchy-Schwarz in that we're multiplying two matrices together, and the norm of that multiplication is less than the norm of each of the elements. But that's a different thing, right? A different structure on this A. This is an algebraic structure, and that has a different name entirely as well. It's called the submultiplicative inequality, and we'll come back to that later because it'll be very useful. But it's not the same thing, so don't conflate these ideas. This is one. They look similar, but they're not the same. One is defined using an inner product, and one is defined using a composition, composing to a sort of a multiplication, right? So very different things. This is not multiplication. This is inner product. So, okay. I mean, when you're drawing block diagrams, right? You never multiply two signals together, right? What would that even look like, right? Multiply. We add signals together, right, all the time. We subtract signals, but do you ever see two signals multiplied by each other? No, never happens, right? No. That's not part of block diagrams, and it's not part of block diagrams for a very good reason, that signal spaces are not in algebra. Right. So now let's move on to systems. Right? Signals are a generalization of vectors, and systems are a generalization of the concept of matrices. Right? So what structure are we going to impose on our systems? Well, the same structure, it turns out, that we impose on matrices. But, and here I'm skeptical that everyone has had a course on matrices where all of these concepts are defined. In particular, have you thought about what is the size of a matrix? What is the norm of a matrix? Well, we defined one, of course, right, in this class already. The singular value, the maximum singular value of a matrix is a norm. But have you seen other ones? Well, there's the Frobenius norm of a matrix, but I'm guessing that almost everyone has not worked with the Frobenius, and I'm guessing very few of you have actually worked with the maximum singular value norm of a matrix. So matrices do what they do. They turn vectors into other vectors. And we've often worked with norms on vectors, but I'm guessing relatively few people have worked with norms on matrices. And it's because there are lots of them, and they have nice properties, but they're a little bit more abstract. It's harder to understand what they mean in terms of system, right? Because the matrix is actually a representation itself. A matrix is not actually those numbers, right? And you can see this with the SV decomposition or unitary transformations and so on and so forth. A matrix is not the sum of its numbers. The matrix is a linear operator. It's a sum of its properties. Right? And so norms, or good norms on matrices, are defined in terms of what they do and not how they're represented. Right? And so this is true for the maximum singular value norm as well. Although in the SVD decomposition we can figure out what it is, you can't just look at a matrix and figure out what the maximum singular value is. I should label this. Right. So, okay, we've actually defined what the maximum singular value was for matrices, and you may not remember it, however, right? Maximum singular value is, of course, the maximum singular value, but it also defines a property of the matrix, which is basically the maximum extension of that matrix. Right? So if you look over all vectors, it's the maximum length of the output of that matrix divided by the size of the input of the matrix. Right? And if you restrict your vectors, the input to the matrix, which is a vector. Right? So both of these are vectors. And this is a vector norm. Right? And so the maximum singular value is the maximum Euclidean norm of the output of the matrix, y, divided by the norm of the input of the matrix, x. Okay. So what then is the extension to systems? Because remember, we think of systems as a generalization of matrices. So if we have an input to a system and an output of the system, right, and we've generalized u and y to be vectors, right? So an obvious norm for a system G then, or I guess we're calling it P, is this same norm, right? The maximum size of the output, which is y, divided by the size of the input, which is u in this case, in my block diagram at least. Now, of course, for matrices, the maximum singular value depends on the vector norm, and actually there are lots of vector norms, but the one we usually work with is the Euclidean norm. I'll choose a different color here because I'm getting bored of that color. Should I choose green? Purple? Let's go purple. Right. The Euclidean norm is the one we all work with. Right? In systems, however, remember we had lots of choices for our vector norms, which is really a signal norm. So it could have been L2, L1, L infinity, etc. Right? So we could define y, and we could even define y and x differently, right? Because maybe our system takes something which is finite energy in, say, L1 and produces something which is finite energy in L2. So these can be different. Right. Usually we don't make them different. Usually they are the L2 norm, right? But it is possible, and in fact some of the results at the end of this lecture do hold for different LP norms. But those are the only ones in the course, right? So 99% of the time in this course, those x's and y's will just be the L2 norm. Right. So equipped with this definition of size of a matrix, right? So we can now estimate the size of a matrix, or a size of a system by extension. We can define a vector space of systems, right? A vector space of systems, right? You add two systems together, and it's obviously what it should be, right? You want to add P and K together, for example, right? Our output is PU plus KU, right? So it's a vector space of systems is fairly obvious. But again, the systems are not a signal space, right? We define a vector space on them. That's fairly easy. But we would like now to make this a norm space as well, right? So we want to make it not just a vector space, but a normed space as well. And so we have to define our norm. And so this is how we're defining it. This is the norm we use for systems. And it's the same norm we use for matrices, assuming that we're using the singular value norm for matrices. So that's the norm. So we have a vector space of systems. We made it a norm space of systems by adding a norm, and you can verify that this satisfies all the properties of a norm. And now we'll just give it a name, because of course it depends on which norm we choose for x and which norm we choose for y. And generally they'll both be L2, but in certain cases they may not be. So this is just a nomenclature for defining which set of systems we mean. Right. So first of all, of course, right, we defined our norm space in this way. Obviously, we have to verify that it satisfies the properties of norm. I'm not going to do that. It's fairly easy to show, but I'm not going to do it. Right. We do have this little bit, I will use this term induced norm, right, regularly to differentiate it from something which doesn't have this format, right? So this is an induced norm. And it's induced in the sense that it's induced by the norms on the vector spaces. Right? So a matrix, right, maps a vector to a vector, and so the definition of the size of the matrix, or the norm on the matrix, when it's defined in this way, is induced by the norms on the vector spaces. Right? So that's what we mean by an induced norm. Another way of thinking about induced is something which is defined by what it does to the vectors. So the properties of the system, the properties of the matrix, of that map, not the representation of it itself, right? The representation of P never appears here in this norm, right? This is in contrast to things like the Frobenius norm, where it's just the sum of the elements of the norm, which is not a very useful norm, I should say. A little bit more notation. Very often, we hope, at least, or we're looking for systems which map a particular vector space back to itself. Right? So something with finite energy to something which also has finite energy. Finite energy signals to finite energy signals. Right? For systems which satisfy that property, we can use this little extra notation here, Lx, right? So we don't have to write down x twice. Right? But that's a very particular case. And it's a very important case because remember, if we're drawing our block diagrams and we have spaghetti noodles everywhere, right? It's important that u be in the same space as y. Otherwise, when you add u and y together, what space is z in, right? Right? If u is in L1 and y is in L2, which space is z in? Well, it gets very complicated very fast, and these block diagrams become next to useless. So we're going to mostly work with systems which preserve sort of the structure of their signals. So they map L2, and for the most part, to L2. However, that particular property is not required for most of the work that we do, in this lecture at least. In particular, even if it doesn't map the set space to itself, it's still what we call a Banach space. Right? So a Banach space is really synonymous with a normed space. And a Hilbert space is really synonymous with an inner product space for most of the purposes of this course. Why do we then give it fancy names like Banach and Hilbert? Well, mathematicians love to label their spaces. And it gives us a handy-dandy way of differentiating what's called a complete norm space and a complete inner product space from one which has less structure on it. Basically convergence. If you have a sequence of systems which seems to be converging, it will converge to a point in that space. And if it's not Hilbert or it's not Banach, that won't happen. All right, so it's important for convergence, but nothing we need to worry too much about, or nothing we're going to study too much in this course. So when you see Banach or Hilbert, that's a fancier normed or inner product space where you have convergence properties. You can prove if things converge, they converge to a point in that space. It's important. All right, so we have a norm space of systems. We have a norm, we have a vector space. It turns out, well, systems, well, we need a little bit more. Unlike signals, systems can be multiplied together. And it's obvious, right? If you're doing your block diagram, right, you have U and P, and then you have G, the output of P goes to G, and that produces Z, right? So there's an obvious concatenation or composition of systems where Z equals G, P, U, right? So we can compose two systems together in series by taking the output from one and putting it into the other, right? So two bits of work have been done on U, first by the operator P, and then by the operator G. Right? Here I use G1 and G2, but we can, well, all right, I'll do G1 and G2. Right? So obviously, right, if G1 maps X to Y, G2 needs to map Y to Z, right? So the input space from one system has to match the output space to another. Similar to how we need compatible dimensions in matrices, right? We can't have a skinny matrix and compose it with another skinny matrix, right? This size has to match this size, right? We need R n by m and R m by p, for example. Right? So the dimensions of the matrices have to match, and likewise the input and output spaces of the system has to match. And so that becomes important. Even if all these are L2, right, the output of the system may have a higher dimension than the input space, for example, and that's very common. And so those input spaces have to match up from block to block. Right? Unless, of course, you just want to draw lots of lines, and then they're all scalars. You can do that as well. So we have an idea of multiplication then, a definition of multiplication. composition of systems, right? And we know which space, right, that should lie in, right, should map X, and now we've eliminated the intermediate Y, and it maps X straight to Z. Now, for this to actually be what's called an algebra, right, we need this submultiplicative inequality. So we have a norm space, and this composition to be actually well-defined, we need that the norm of the composed elements has to satisfy this submultiplicative inequality. So that the size, the norm of the composed system is less than the norm of the first, well, here's the first system, times the norm of the second system. Right? So this is the submultiplicative inequality, which we talked about on a previous slide. Okay. And if you have this, right, then the composition multiplication thing you defined is well defined, and we have this algebraic structure that we can then work with. So now what? Where do we go with this? Let's see. Some other things here. I think mostly I referred to both of these already. Again, there's that Frobenius norm, which is defined by the representation of the matrix and not by its properties. Right? That's just the sum of the elements of the matrix. It's actually just a generalization. If you took all the columns of the matrix and you line them up into a big vector, right? That's basically what they're doing here with the parent Frobenius norm. And likewise, if you represent this as the column version of M, right? It's a vector, and so you can define the inner product space, but it's next to useless. So we don't work with it very much. It does define an inner product space, but not in any useful sense. Nothing we can work with. So we're going to ignore the Frobenius norm on matrices for the most part. All right. So now we've defined sort of some basic concepts. I'm going to break for just a minute, and then we will talk about some transformations on those spaces, some additional vector spaces.